So I repeat because it just started recording. I would like to start this class by asking you if you have any issues with the first or the second lab, the ones that have already approached that lab. And let's start with a short discussion about those things, and then we'll continue with the actual class. I'm asking that because I had a couple of questions over Teams, which is good. Which is good. It's better than asking them by email because it's not that easy to track all your emails and see to whom and when I answered. But as I had a number of questions, so my question now: do you have any difficulties with the first two labs?
In my opinion, it wasn't necessarily difficult. We
Yeah.
just had a steep learning curve because, for example, we haven't done multi-threading in Python so far, and we had to learn the syntax first. But besides that, it was manageable, I believe.
The question is not if it was difficult, but more if you had any difficulties with it. As mentioned in the webpage of the class, this lab is mostly, or its main purpose is to learn you how to approach network programming. So the first thing is to actually get you used with the API of the socket interface. And then the second thing and the most important thing is to learn how you need to represent different data types and their in-memory representation when sending items of those data types over the network. So this is the most important part of the first lab. There are these two main things to follow here. Data conversion for the network transport and the API interface. So the problems are, let's say, they're not even on the medium class of difficulty. They are easy and very easy problems to solve. The main things is to, or the main purpose is to get you to get with your hands on programming. So it involves sending numbers, sending strings, sending arrays of numbers, and doing something with them on the server side and sending back some results. So if there are no issues with that, I will. Well, let's continue today with the part where we start last time, and I will just stop me at any time when you have anything to ask. We've seen this part with the socket addresses. Okay, remember we said last time that there is a structure that you will manipulate at each and every application you will design using networking API, and that's the SOC-ADDR structure. This one here. This is the generic one, which somebody told me last time that it doesn't exist anymore, and it's probably not exposed. Sorry. Maybe not exposed directly. Okay, so maybe you don't see this anymore. On Linux system, it's some Linux systems, because I tried it last time when we discussed it, it is still exposed. I mean, you can declare a SOC-ADDR in structure as a variable that you will use like this, but declare like this. It is still possible in some Ubuntu, I think 18 and 16.04, they all have it. Fedora, I don't know what version still has it. So probably they are phasing it out. It's still there in the operating system, that's for sure. It is maybe not exposed to you, but that's not that important.
Windows has it as well.
Okay. So it might be phased out in the way that you don't really use it like this. Okay. like this, you don't really use it. It's just that this is a placeholder for all types of socket DDR derived things. This is, you can think of it, you can think of it as a sort of OP style at the OS level. Interfaces where this thing is actually a specialization of this structure here. But as these are only structures, they don't have methods. Only that at the binary level, if you look inside, the SA data gets mapped to a number of fields in the more specialized version, and so on. And we can have specializations not for IN, which stands for Internet or TCP/IP protocol. We can have specializations for other types of protocols that will use different things here, these fields here, which get mapped over this thing. Okay, so I won't insist on this because I don't want it to be boring. What I haven't said last time about the APIs is that all these APIs here about networking when sending data and receiving data are by default blocking. So by default, these are blocking, which means whenever you call send on TCP, okay, when we are talking TCP right now, when you are calling send or you're calling receive, as long as, for example, receive is the easiest to explain, as long as the other party didn't send you any data yet, your receive call will stop there. Your application will stop there, and it will not advance until something is received over the socket. Whenever some data is available to you, this call will return, and it will return to you the size of the received data, and it will return you this. Sorry. This as the actual, this as the actual data. Now, pay attention because I didn't have time to explain this last time. Take a look here. You see the data type which is passed in as argument here and here. Networking has nothing to do with data types. It doesn't know data types. It doesn't care what you put inside. It just takes a void pointer, which means you can pass in an integer, you can pass in a single char, well, the address of an integer, of a single char, an array, a structure. You can pass in a string in the C, let's say, from the C point of view. The networking API won't care. What it does care, and or what is important here is that data will be taken. You pass in this, in fact, void pointer. You have your memory. And I'll put it like this. Suppose we have a short int here, and I'll put 000F hexa. And if we take, we say this is 0 and increasing memory addresses, okay, RAM. And then suppose we get a string, something like 0. Okay, 8, like that. So we have a string written like this. If you pass a memory, that memory address here, kind of reading from right to left right now, but this is just because this is the way I've drawn this thing. If you pass this memory address here, this one, and you say send from here 1, 2, 3, 4, 5, 6, 7, 8, okay, and it's 8 bytes. So if you give 8 as length to a send call, it will send both these items together, all together, if they arrange like that into memory. It will send the entire string plus this short int here on 2 bytes, which has as value 15, 0f. Okay, you can pass in through the network both these items with a single send. Now, on the other side, on the other end, it depends how you read them in order to be able to interpret the exactly the same thing, one string plus a short int, or you can divide it differently. But this is up to you. It's your convention that you do when you design your applications. Okay, this is important for you to remember. And keep in mind that read and write are blocking. So read doesn't return by default until you get something. Now, there is a question, when would send be blocking? Send is also blocking. Normally, it won't block, and most of the times, it will return immediately to your application. But if you send, for example, a very large chunk of data, suppose you send 100 megabytes of data or 10 megabytes of data, one single shot. You declare some array with 10 megabytes of data and you send it over the network. Well, your send might be blocking for some time until it completely sends. It might not send the entire, okay, if you put 10 megabytes of data. You ask it, in fact, while you give it here, it's a buffer, and you ask it to send 10 megabytes, whatever that gets translated as a number. That's 10.24 kilobytes times 24 bytes. That's the amount of data you should put there. What you do with this call, and you need to remember this when programming, is that you pass in this buffer and you ask the networking API to send the entire data. It will probably block for some time, and it can return you three things. Something negative, which means error, and that your socket is done, you cannot use it anymore. There has been some error in sending that data. It could return something larger than 0 and smaller than 10 megabytes. That means it has succeeded sending some data, but not all of it. And it can return something equal to 10 megabytes. But basically, these are the options that you get. If it sends something, if you're in this case, it means you need to call send again from the offset in your buffer, represented by the return value here, the amount of data that has been already sent, and continue and retry sending the remaining of the data which TCP hasn't been available to deliver to the other side in one shot by calling send multiple times. Okay, so you need to pay attention to these scenarios. The fact that it returns something positive, it doesn't mean that it has succeeded sending all the data that you have sent. Okay, pay attention to that. Now, that won't normally happen with 2, 3, 4, 6 bytes or so, usually, but you need to check, because depending on the state of the networking infrastructure on your operating systems, you might have lots of processes contending for the network that are trying to send and receive data, and depending on how many processes are and how much data they are trying to send at any given point in time, you might not be able even to send a single integer. It might be divided into 2 sends, okay, 2 bytes plus 2 bytes or something like that.
Isn't send supposed to be atomic?
Yes, it is atomic, but it doesn't guarantee that it sends all the data. It is atomic from the point of view that it sends something or it returns an error. Usually, you will never get a 0 out of it. Okay?
Because on Windows it says that if the data is too long to pass atomically, then it just throws an error.
Normally, it should send some data. I haven't seen it even on Windows, even if the documentation says so. I haven't seen any case where it returns something negative, but it might. These types of implementations are specific to each operating system. So most of them try to agree to some well-known protocol, and the de facto standard is that it tries to send as much as it can on TCP. So if some particular implementation, and if you look in the Windows MSDN documentation, you get the documentation for WinSock 1.0, 1.1, I think 1.2, and 2.0, 2.2. So even between those different versions of the library, you might get different behaviors. So you need to look at the behavior specific to your library. And that's a good remark. Pay attention to the documentation at each time. It tells there what you should look for whenever you call that API. Okay, so that's about send and receive. Pay attention, they block your application. And if they block your application, that means you cannot start a send and then continue something else. Or on the server side, when you're waiting to receive something, that means you can't handle other clients, for example, because your applications will be blocked, waiting for something for somebody to send you some data. And if nobody sends you some data, well, then your server is basically blocked there. That's an advantage and a disadvantage. Well, I won't go over a client-server iterative example, or maybe I can on a very simple one. Keep the drawings. And if we go very fast, you just tell me if you need any explanations on any. So there was some part of the code that the simplest thing that you can ask from a server, for example, is to compute the sum of two numbers. So I won't insist on the first part where you check out, you connect to the server. Okay, connect is a blocking call as well. So pay attention to this. In the client, it won't return until it connects or it fails. So after this call, you either have a connection, and you should think to a TCP connection as being like a pipe. Only that pipe, it's not usually on the same machine, on the same operating system, but it goes between two machines over the internet. But otherwise, it behaves like two glued pipes, one for sending and one for receiving. As if you remember from the operating systems, you needed to create two pipes in order to be able to send and receive data at the same time from the other process. So the TCP socket, it's like you have two channels in one. You can send over it, you can receive over it. But you need to agree on the fact that at some point in time, you're trying to read from the socket, and some other points in time, you write to it. And you need to agree on that to the dialogue with the server. If both are waiting for some data from the other party, then neither one will advance. We will take a look at that. So the simplest case, you read to integers from the standard input. Do you see? Is it big enough? The fonts are big enough for you to be able to read the code?
Yeah.
I can make it a little bit bigger if you want. So read to integers. Then anyone or everyone remembers what these two calls are needed? We will discuss about this today, in fact. I translate here the local representation of my number to a standardized network representation, whatever that is. Okay, I do that host to network short because my and this is I have a problem here because these are 1.3.32, so they should be long here. And send over the network. Take a look here. I just pass in the address of the integer. I don't care if it's an integer. Sometimes, if you compile it with a C++ compiler, you might get forced to cast it to a void pointer here, not with a C compiler, and not with all C++ compilers. Okay, sending A to the other side. I didn't check for errors here, but normally I should check if the rest value is negative or it's less than size of A. And if that's the case, just try to send again. And then send the value of B at the same time and wait for the result from the server. Now, what the server will do, my server here is the one we've discussed it over the labs, I think. It accepts in a busy while loop. It blocks on accepting clients, and whenever one client is accepted, it reads to, I might have an error here, what are A and B's? A and B are declared where?
In the while.
In the while. I have here, there's an error here because I shown that during the lab. uint16. Now, in the client, my variables were full integers. You want to have on both sides the same data types, because if you don't have them, you will get spurious errors because of because the data will be truncated and not interpreted in the proper way. So if you have full integers on the client, you should have full integers on the server and vice versa. And by using this thing here, I am I'm not using the length, I'm using the size of my data type for fixed size data types. It's easier to write it like this because whenever I change the data type, the size of that variable will fully reflect the new data type there. So I don't need to change the code. So I change the type, but the remaining calls are staying like they are. I'm reading back an integer, another one, convert them back from the network to the local representation. We will discuss this and I'll tell you more. Compute the sum, convert the sum back to network representation, and sending over the socket to the client. Now, what can you tell me about this server implementation from the already experience that you have with the first lab? Are there any issues with this approach, if any?
Yeah, first we are using host short instead of host long, but that can be fixed.
Yeah, okay, so that's but that's already an error. It's a logical error. We might not get what we expect here. If I'm sending an integer, a full integer from the other side, if I do network to host short, it will definitely not get the proper value back here. Firstly, because network to host short operates on 2 bytes and I've got 4 bytes, so definitely I will not be able to get the proper version. And well, starting from that point on, nothing will be correct. Any other things, any other issues that you see?
And because we are using sends and receives, and those are blocking calls, that means our server can only serve 1 people at a time.
Exactly, that's a very important thing. While I'm doing this, try to go to the client, send A, for example, I put a sleep, a very long sleep here of, I don't know, 10,000 seconds, 20,000 seconds, and try to connect with a different client. You'll see what is happening to the same server. That's a very good remark. Any possible solutions to this?
Using threads or other processes?
Yeah. This, in fact, it's made simple by the fact we see now why accept won't use the same socket after accepting a client, but it returns a new one that is specific to the very client that has connected. Because that will enable us later on to actually create processes or threads that will handle that specific connection with the client that has just connected, enabling us, for example, in the parent process, that is this one. So after the client is accepted, I am able to create different threads, to create new threads or new processes that will handle that client through that socket. And I will keep using the rendezvous socket just for incoming connections. Okay.
Sorry, can you explain again why was that wrong and was only good for one client?
Why this is only good for one client here?
Mm-hmm.
Okay. So suppose I am running my server here. Okay, bind, listen, while one, accept. When I get here, this call will be blocking. So as long as no client connects, my server will just sit there. Whenever one client connects, this call returns, and my server will start reading from the socket in the same process, in the same thread. So if my client and it's not sending data right away, I will be blocked here. I will block here and block here until the client is willing to send me some data. During that time, I am not able to accept any other client because accept is not called. And if one of my clients is misbehaving, well, I'll be a sitting duck here, just waiting because the client is misbehaving. If the clients are, and your question is good as well. I was just about to tell you this thing. So it's a very good question. Let me just display your guys because I don't see who asks the questions. Who is asking the questions at all times. So if the client is, where is my presentation? Oh, it's on the other screen. Okay, but just one moment. Okay. Okay. So if my client on this particular implementation of a sum of two numbers are well behaved, which means as soon as they connect, they read two integers and they send it over the socket. Then everything happens, let's say, in a acceptable way, which means if the client is reading two integers in a row very fast, I mean the user is there and its input it's fast, or if you're reading them from a file, so there is no user input, you're not linked to waiting for a user to do something, then this type of implementation, which is called iterative, we will discuss it in a minute, this will do just fine because the client is getting data fast, it's sending data fast. These things are very fast operations. These in terms of CPU time will be milliseconds to do this stuff. Read data, convert it, do the sum, send it back. So in a matter of a few milliseconds, all these things here will be done. And then the server is getting back to accepting new clients. But if these operations here or could take a longer time, well, in that case, the accept call will not be called again fast enough for other clients to be able to connect. And was I clear here, or is just still a cloudy, shady thing?
No, I think I got it.
These are not complicated stuff. It just helps you to understand why things are happening, within the way are happening. Okay, but otherwise there is nothing new under the sun. The same thing happened with you for you with pipes. With a pipe, if you started reading from a pipe and nobody would send anything, then you will be blocked there. It's exactly the same behavior. Okay. Only here, you also need to accept a new connection in order to handle different clients. With pipes, you had them implicitly because the parent process created them, and then the child processes had them, and they could right away communicate with each other just by inheriting something. Inheritance is a good thing, like it is in, let's say, real estate. You get something for your parents, you will get a place to live. So that's a given thing. Okay, here it's not a given thing. In order to be able to actually talk with a client, you need to accept it first. Okay, and this is the first type of implementation. Let's go back to, where is my presentation? Yeah. What do we need to remember about TCP? Well, we need to remember that it is connection oriented, which means you need to accept connections before being able to talk to clients. Well, this just resume what I told you about send and receive operations, that they will actually return errors whenever something happens. What you should remember that with TCP you get guaranteed data delivery, which means something that has been reported by the send operation as being sent, it will eventually reach the other side. You get guaranteed data ordering delivery, which means if you send 2 integers in a given order, they will be received on the other side in the exact same order. A and B, if you send them in this order, they will be read A and B on the other side and not B and then A or something differently. And you need to pass this argument to the socket call. This is TCP. Now, we have already approached, and this is the paradigm we will mostly be using when implementing, but not all the times, remember. This will be the programming paradigm that will be used throughout most of that you'll probably even use in real life throughout most implementations, is the client-server approach. You have, and with this approach, what we have a server which is nothing more than an application that implements some service, and it provides that service to third parties. And those third parties are clients that are, let's say, more or less, if I can quote that, taking advantage of the services offered by the server. That means they are consuming them. You connect to a server, you ask it, you give it data for the task his ability to do, and it will do the task and it will return it back. It will return some answer back to you. And from this approach point of view, we can classify the server types into 3 different major categories. The first one is the one that we have studied already, iterative servers, blocking. Blocking means that the TCP implementation of accept, read, call, connect, send are blocking. Then we have the second approach that we will see in a minute. It's concurrent servers, which can, based on the same API behavior, because we will see that this behavior might be different. And we can set up, I open a parenthesis here, the socket API could be set up to be non-blocking, but then the behavior will be completely different. We will see that. So with a blocking approach, when all those calls are blocking, the concurrent servers are some types of servers that are actually being able to serve multiple clients at the same time. And they do that by using either fork or threads, as you have already told. This is the second approach. On the complexity, let's say, on the implementation complexity scale, this is the second approach. And then we have the third approach, concurrent multiplexed servers. These ones, there is a special API call called select that we will be learning probably next time. I'm not sure we have time today, because I have some examples to show you. So this is yet a different way of approaching networking that allows us somehow by using a single process or a subset of processes, but not exactly the same number of processes as you have clients, to handle multiple clients at the same time. So remember, iterative, concurrent, and concurrent multiplexed. The first approach And now, of course, let's stay there, because I would rather ask you this. When do you think will we use any of these approaches? If I'm asking you to to implement the application, that the code that we've seen before, let's have a server that computes the sum of an array of numbers. Would that be using, and I want that to be concurrent, a concurrent implementation. What approach will you be using, fork or threads? And if you give an answer, I would like motivation. I mean, I would like an explanation for that.
Well, it's a good question because it kind of depends on what you want to do. Forks usually copy the whole program, but the program isn't that large, so it could be done. And you don't risk crashing the whole server if one client crashes your forked program. But with threads, if the program crashes, then it crashes the whole server. But you have the advantage of not using that much memory.
Yes. So fork, there are some disadvantages from the point of view of the memory footprint. Your entire process will be duplicated and it will start executing from the next instruction after the fork call. Threads, on the other side, a little bit lighter than fork and processes, but if your implementation crashes at some point, it will crash the entire server down. I mean, it will actually stop working for all the clients that are currently connected. But there is some other thing we should pay attention to. What about what if I'm sending, for example, from multiple clients strings or subparts of an array, and the server needs to actually concatenate those arrays together, sort them, sort the entire array, and send back to each client the sorted array.
In that case, that would be better to use threads, because then we can access the same memory.
Yes, do we need the shared state or not? Yeah, that's the question that you need to ask yourself whenever you implement something. Do we need shared state or not? If we need shared state, well, you can do it with fork, but you can do it with fork, but it will definitely be more complicated because you need to fork as many processes as you have clients, and then you need to actually communicate back with those processes back and forth to exchange the data that is coming from the clients with some central unit that does actually the job. So if you need shared state, the more likely implementation you'll have is with threads. If you don't have a shared state, then you need to put in balance. The advantages and disadvantages that you would have of threads over fork. If the amount of memory that you get access to is not a problem for you, fork would be the easiest implementation and the implementation to go with. If that's not the case, then you could actually take a threads implementation when there is no shared state at all. Nothing stops you to do that. Okay, so in practice, with no shared state, you can use both approaches. If there is a shared state, you'll most likely go over the thread implementation. We will discuss about this one later on and see what its advantages are. But basically, remember, these are the three types of implementations. So the first one is based on fork or on Windows. On Windows, you don't have the fork call exactly with the same behavior. Process management is a little bit different. So you need to create a different process. And that process, you need to pass it over the handles to the socket that has just been created. It's not automatically like with fork. You just fork a new process and it inherits all the script file descriptors from the parent process. You could instruct it to, but this is something you need to do especially for that. Threads, as we discussed, when you have shared state, and select, it's a different system call. It's like socket. You have select. Okay, these are two APIs that are working. So it's at the networking layer. Now, do I need to explain this? This is because I just wanted to make it official. You know, if I've used in 2 or 3 examples that I've presented you, the get host by name call and get host by ADDR call. These are 2 calls that are doing this. Linux.csc.ubb.cluj.ro, the first one. It gets translated to an IP address, for example, 123.30.0.4. The other one, the second one, does a little bit the vice versa. Sorry. 172.30.0.4. When you get an IP address like this and you want to know what will be the most likely name used by that machine, it helps you, not all times, because it's not all times capable to do that. It depends on how DNS servers are configured, and this is a point that we will learn later on. Both of these calls are using DNS, the domain naming system, which is a service implemented at the networking layer. And the first one translates from machine names to IP addresses. The second one translates from IP addresses back to machine names. It is not mandatory that you get, if you do the translation or the function, if you look at it as being a function, is not necessarily, how should I put it, inversible. That means linux.csc.ubb.cluj.ro translates to this IP address, and if you want to translate this back to a name, it's not necessary that you'll get this name. You might get a different name, but it's a different name from the same physical machine. Okay, so if you, for example, you could get not this, but www.csc.ubb.cluj.ro. Why? Because you could have a machine with multiple names, but the number of IP addresses is fixed. It's not usually the number of network interfaces it has, or something similar to that. Any questions here? So this call takes a name or an IP address, and it returns back a structure like this, where you get inside, no matter how you called it, with a name or with an IP address, you get back a name. Let's say the official name of the host. You get some other names for the same machine, and you get an address list back, which are IPs. You could get a list of IPs here. You see this is a char pointer. It's a list of lists. Is or an array of arrays. So whenever you ask information about a machine, you get back a list of IP addresses if that machine has multiple IP addresses, and then you use whatever IP addresses from that list you want, or whatever name from that list you want. But usually the socket APIs are using IP addresses at the lowest level to communicate, so usually you take those and use those. Any questions about this thing? It's nothing fancy, nothing complicated. Whenever you want to be generic enough to, in order to send to your application, to allow your application to actually use either machine names or IP addresses, you will be using this call. Okay, that's it. So if there are no questions, let me, what time is it? 3 minutes. Let me shortly go over before we start studying memory representations, this thing. And I want you to pay attention next hour. Let me show you concurrent implementation. Keep this. And if we go back, it just happens in the server. So server concurrent. Let's take a look at what is happening. The initialization part, it's exactly the same. I create a socket, bind it, listen, and I won't insist on it. I have the same while infinite loop, then call accept, and then fork. This is the fork implementation. Now, if there is some error, you just display the error, and then probably you cannot handle that. You should handle the error here, handle that typical case here. Handle the situation in some way. Because you got the client connection, but probably you're out of memory on the server, so you cannot handle that. Either you wait a little bit more and then you try to recreate the process, or actually you close the connection. You send back a message to the client and you tell it, okay, you don't have enough resources. Then in the child process, close the rendezvous socket. It's exactly as with pipes. You don't use that socket in the client. And in the client process, pass this socket client, the client socket that has just been created to a function, in my case, that will actually do the entire implementation. Read two integers, 32 I said they were. Do this like this, because we changed in all places that. Do the sum and send back the result and close the client socket and return. This returns here into the client process, and you definitely need to call exit. Okay, if you don't call exit here, that means your child process will continue concurrently with the server process, and they will both call accept. You'll have two processes calling accept on the same socket, and whenever there is a new incoming connection, just one of them will get it.
Well, right now the socket is kind of closed, so it will just loop indefinitely.
Sorry, okay, because this was closed here. Good remark. So here you'll get an error when you call this accept. In the child process, you'll get an error here, and then as it didn't handle, you should handle that error here. Handle sock client. Okay, that's as being for teaching purposes. If I don't want to get 3 pages of code just for one simple sum implementation, I didn't handle all these errors, but normally in industrial implementation, you'll handle all these errors. You'll never have a system call without checking the return back. Okay, so that's all of it. You need to exit, because otherwise you'll create a tree of processes which will just live into your operating system, and some of them do nothing, some of them trying to do stuff which they're not supposed to do, and that won't be a correct implementation. Or you could just call exit here. Okay, that will be possible, yet let's say not so semantically correct, because what is happening here when you call this function is that some arguments are passed on to the stack And we learned that whenever we allocate any resources implicitly or explicitly, we need to deallocate them. And if you exit here, of course, they are deallocated because your process is destroyed. But if something bad happens, okay, normally what we try to teach you is that whatever you allocated, you try to deallocate exactly into the same order. It is actually correct to do this here, but not, let's say, not as correct from a teaching point of view, because I teach you here that, okay, you allocated resources by calling this function, you passed in something into a stack, and then you just exit abruptly that process, not unwinding that stack, which gets deallocated eventually, but that's why I implemented it this way. So it's as simple as that. Fork, it's nothing very complicated. Okay, any questions? Or let's take the questions after the break. Let's take the break, and I'll take questions afterwards, and we will discuss about little endian and big endian and stuff related to that. Okay. Okay, I'll see you guys at yes.
I just agreed.
Okay, sure. Okay. Okay. Let's take a short break, and we'll be back afterwards. Okay. So I'm back. I'll continue. Can we, or just tell me, let me know if we can continue with the class.
Yes, we can.
Yeah, I guess so.
Okay, any questions? I mean, these are very simple things. I don't want you to get bored because I'm presenting in too much details. Hence my questions. Do you have any questions about this thing? I suppose no, because, but if you have, feel free to ask them. I suppose no, because the implementation is quite simple. I mean, it's exactly on the same pattern as you used when you did pipes or the name pipes or stuff like that. It's mostly the same thing. I would say 95% is the same thing. The rest of it is just details. So you do approach this with fork exactly in this way. The pattern of your server implementation will always be the same. You'll have an infinite cycle, infinite loop that creates new processes whenever a new client is accepted and then handles those clients. So what is in mind? Yeah, I've heard something. Okay, so let's move on. First, but before moving on, what do you think will happen in this case here if you have 20 clients connecting exactly at the same time?
Well,
It will
first they
put them
wouldn't.
into a queue.
Yes, we set up this here with a backlog of 5, with a length of 5. There is some question in the chat. There is a question. Shouldn't we wait for the child processes in order to avoid creating zombies? Yes, I mean, I didn't put this thing here. It will make it longer, but but you should know that the wait call is also blocking, so you need to manage that. If you wait for a child process, you could do that by actually trapping the sick child signal and wait for the child there, because otherwise the call, if I put it here like this, wait like this, well, haven't done anything good, because if one of my child processes is misbehaving, I mean, it's not actually finishing here correctly, then my wait will be blocking here, which means I won't be able to accept new calls and so on, and the story continues exactly as in the same way as in the first case. I couldn't accept new clients because my implementation took too long. In this case, it will do exactly the same thing, but not because of the logic, because I'm just waiting for a process to finish, and that process is not finishing. So you need to pay attention in how to handle things about that here. Any other things you should pay attention to? Well, basically you should handle all errors, and I think with that, and properly wait for processes. Are you familiar with signals? I think you have, because you studied operating systems. So one way to wait somehow asynchronously for child processes is to catch the sick child process and then wait for that process which just has died there for that child process there, and that will actually take it out of the zombie list, and it will release all its resources, and nothing bad will happen. Now, if we move on, is there another question? No, don't see. If we move on now, example fork, that was it. Let's discuss a little bit about little endian, big endian, and stuff like that. It's nothing. I mean, I think most of you remember from the computer architectures what is this? Wait, I'm not allowed to. Hey, come on. I want my laser and I want my pen. Back. What are you doing? Something happened with the pen and it's not allowing me to write anymore. But we'll continue like that. In color red. So I think most of you remember what little endian and big endian mean. It's nothing about Indians. It's about ways of storing data into memory by different CPU architectures. And there are two major approaches. The big approach, this one, and the little endian approach. And the name comes from big and in, well, and DNS, and little and in. And it tells us about which part of the number is at the lowest memory address. And you should know there are two types of CPUs. If we should classify CPUs, by the way, they represent numerical data types. They will be big endian and little endian. Some of them use one approach, some others are using the other approach. And why does it concern us in computer networks? You should know to answer this question by now. From what we've discussed the previous hour of this class.
Sorry, can you repeat the question?
Why are we bothered by little endian, big endian things on CPUs in computer networks? They seem to be nothing, to have nothing related to each other.
Yeah, because some computers work on little endian architectures and some on big endian architectures.
Okay,
so we communicating through a network must not differentiate between the two. So we must be able to work with any architecture.
Yes, because I just told you that the send call, it does not is data type unaware. It takes a bunch of bytes from a memory address and shoves it off over a pipe over the network, and it takes it out on the other side and puts it and lays it out on the destination memory at the destination memory address exactly in the order as they came out of the pipe. Now, if the memory representations from the source and to the destinations are different, those two entities represented in memory exactly in the same way will have two different meanings. And okay, in little endian order, if we are representing RAM, oh, come on. From max to min, from 0 to max, whatever, megabytes. That means that when you send a 2-byte entity, at the lowest address, you'll have the low order byte, and at the highest address, you'll have the high order byte. Okay, for example, if we send as an example, let's take I mean, we should always position ourselves in one of those representations because that's, I mean, we cannot be between representations. We're either little endian or big endian when we're looking at a number. But suppose I take this thing here, 0, 0, 0, 1, H. Okay, these are bytes. So this is exactly the value 1. When I put it here, it gets, I have a byte of 1, sorry, I have a 0, 1 as values, and I have a 0, 0 here. If I take it like this and sending over the network and lay it out in a big endian architecture, exactly in the same order, no, so I didn't do that. Here, the in-memory representation is this. So I have 0 here and max here, max megabytes. So my layout was at the lowest address I had 0, 1. So this one was the first byte to be sent out on the pipe. This one will be the first one to be received. So it will be placed here, 0, 1, and I'll have 0, 0 here. But the meaning of this number will be different on this representation. This number will come out like if we take the same approach, the same convention as there, it will be looked upon as this value, which is nothing more than 65. No, sorry, not 65. It as the number departed from the source would arrive at the destination as being 256 at the destination. This byte here is 0. So this represents the first 255 values. And this one being here on the second byte, it will translate to a decimal value of 256 because of difference in representations. Are you getting this right? This is very important, and this explains.
Yeah, I guess the only problem I have is the fact that the high order byte shouldn't be 0, 1 in big endian representation because it's the lower address, and the lower address would have the 0, 1.
Yeah, sorry. Okay, yeah, exactly. Exactly, and that will, yeah, 0, 1, 0, 0, and okay, you get, we could draw this, I mean, we could draw this, it doesn't matter. I can draw them again if you want, if you don't understand, but the idea is that you get something, you transport it over the network, and you lay it out at the destination. But because the CPUs looks at it differently, it will represent a different value. A little endian CPU, let me just take a bunch of memory and explain this to you. Let's say we have 2 bytes, the same exact 2 bytes, 0, 0, 0, 1. And I don't care about the stuff which is here. If we look at this from a little endian perspective, what do we get? And suppose this is 0 and max. Suppose memory is laying out in this direction on both architectures, and we have these 2 bytes here. From the little endian perspective, what value do we have?
It's just 1.
1. What do we have from the big endian perspective?
It's 100 in hexa.
Well,
so 256.
Yeah, it looks differently. Big endian, it says the high order byte is at the lowest address. So the lowest address is this one. It will look at it and it will say this is the highest. This is the high order byte from my for my short int. So it will says 1 multiplied by 256 plus 0, because this is the value which I have here, plus 0. And this equals 256. And this representation here, I would have, this is obtained by saying 0 times 256 plus 1, and this is 1. So I get this in this representation, and I get this in this representation for the same arrangement of bytes in memory on both architectures. So when the data comes out from the socket, it will just be laid down increasingly into memory in the order bytes are coming in. That's the problem, and that's the main problem that we have, and that's why we need to convert now the numerical values to some sort of standard representation, because otherwise we don't get the correct values, because the CPUs is not looking the same way on the two architectures. Is this clear?
Yep.
Yes.
What if we have 4 bytes?
Same thing would happen, but with 4 bytes instead of 2.
Yeah, exactly. Okay, so if address this way, same thing will happen if we look at it from the big endian or little endian perspective, only that one looks from this. It's like it's looking from this side, the other one is looking from this side. Okay, so exactly the same thing will happen. So hence we need something, because we don't know which architecture each machine is, and we shouldn't be, we shouldn't be bound to know what architecture are we discussing it from the network point of view. Or for that reason, we have these calls H to network X, and I'll put it X. Well, it's something like short or long, and we have the calls N to host X, where X is the same short or long. What do these calls do? Well, because of this difference in the way CPUs are looking at the data, the networking, those who implemented the networking API said, okay, we don't care about how CPUs are looking at the data, and neither of the communicating entities should know about how data is represented on the other one. Instead, what we say, we introduce these functions which will take data from the local representation, which is host, and convert it to a network representation. By standard, network representation by standard is big endian. So if you're sending data from a little endian machine to the network, H to NX will convert it to big endian layout in memory. It will just swap the bytes. If you're on the big endian machine, this call will do nothing. It's just a return the same value. When you get the data from the network, if you are on a little endian machine, this call will swap the bytes again and return the swapped value, the swapped representation. If you're on a big endian machine, this will just do a no operation. It will just return the same value. Now, we call these functions respectively on the source and on the destination machine. And on the source and on the destination machine, we know which architecture we are. Okay, so these calls get translated correctly. If I'm on a big endian, the correct implementation will be here for the big endian machine. If I'm on a little Endian architecture, again, that implementation of network to host will swap the bytes. All the bytes that are passed in are swapped and returned because it knows we are locally on a Little Endian architecture. And with this in mind, you convert the data to the network representation, you convert it back to the local representation when you get it on the other side. Right? Anyone got the idea? Or everyone got the idea, or why do we need to call these things? Yes, no?
Yes.
Yes.
Okay.
Yes.
Okay, so my question is now, you have seen that whenever you fill in the port value in the socket DDR structure, you need to also do host to network, and also for the IP address. You need to do that because all the network networking APIs are working with big Endian representations. So you need to, all the values that are passed to the networking APIs should use these calls. Even though it's not data which is sent over the network, the networking APIs expect whatever numerical data is passed in to be in network order. Okay. I have a question. What happens with float and doubles? We don't have, I am telling you right now, there is no host to network float.
Well,
There
it's
is
on
not.
4 bytes, so it should be still host to network long.
Yes. Yes. But you should know that the float representation is something like this. It's on 4 bytes, and you have a number of bytes. This number here. Sorry, this one is a mantissa and exponent representation. And you have a sign here. And the float value is obtained by doing this formula here. It takes the sign bit. If it's 1, it takes minus, it says, okay, my number is negative, otherwise 1, multiplied by 2 power exponent, this one, this numerical representation here, multiplied by 1 point mantissa, the remaining of the bits here. And you can see that we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 bytes here. We have 1 byte here, that's 9, and the remaining up to 32 are mantissa. So 1.32 minus 9, that's 23 bits of mantissa. And the same happens. With float. Is as on big Endians, this entire representation is flipped. Okay, so on big Endian, the idea is that entire representation is flipped over. And in practice, you could do something like when you want to send a float, sorry, come on. When you want to send a float, in practice, you could call host to network long, and you do, if you have an int, sorry, float. Float A, it's 1.3.14, let's say. We could do something like, we could do a trickery, like you take a, come on, int, like that. You take the address of A and you says, okay, I want to look at that as an integer pointer, and you take and you pass in this. You take and you pass in the content of my pointer, which is a float, but I'm looking at it as an integer. And you can use this to solve your problem. Now, what happens with these things, which are doubles, and we don't have any call to swap, to convert them to network representation? Well,
Can
in
we
this case,
send them int by int, like 4 bytes at a time?
if you send them int by int, and I'm glad you pay attention to this, you'll have this. You'll have this, and then you'll have 4 and 4 bytes at a time, okay? If you send, it depends where, let's say 0 is 1 here, 31 is here bits. If you send them int by int, you won't get the correct flipping, because you will be flipping this thing here. Let's say it's byte 1, 2, 3, 4, 5, 6, 7, 8. If you convert them individually, you'll get what? Well, like you said, you'll get 3, 4, 0, 31. You will get 1, 2, 3, 4, and you'll get 5, 6, 7, 8, and it's something which is messed up.
Yeah, well, now we just have to flip them as well. So the client could know that we send them in reverse order.
No, because you need to actually send for what you actually need to send is this 1, 2, 3, 4, 5, 6, 7, 8. You need to flip the entire 8 bits altogether. Okay, but you can do this in either way. I just wanted to show you the example. You can flip this even manually if you want. You can write your own function that flips an entire 8-byte entities without any problem. But you need to pay attention to this. Okay, now in practice, if you implement this if you implement this once, where am I? During the computer networks lab, you can use that function all the times. In reality, I'm not really asking you to do that all times, because once you do that implementation once, you can use it all the times. In practice, it's just, there is nothing difficult. And as you communicate only between machines which are little endians, you could skip this thing, but you need to remember it. The same happens if you have long longs. There are architectures where long it's int on 64 bits. Okay, so 8 bytes. The same thing happens there. You need to employ exactly the same function. It just takes a pointer to an array of 8 an array. It just takes as an input an array of 8 bytes, and it swaps the order of the bytes inside the array. It flips the array around. Okay, and now let's take an example a little bit more complex. I won't enter into all the details, but I want you to show you an implementation in Python as well, because right up till now I've been showing you only C and C++ implementation. And let's take a game. But before, is it all clear about endianness and why we should handle it? I believe so, but if you have any questions, feel free to ask them now.
I have a question.
Go ahead.
I understand why it can be a problem, but I looked it up, and the x86 architecture is little endian. ARM also uses little endian most of the time.
Who?
So the ARM processor architecture.
Yes.
And is it really a problem now? Because Literally
Yes,
every
because-
modern processor uses little endian.
It's not every modern processors. You have CPUs which are used in, let's say, you still have CPUs which are big endian. It's not that ARM is using little endian as well. ARM is using, you have ARM, Intel, and AMD. They are all using CPUs. But the problem is that you want your application to be correct in all possible CPUs. And if you take a mainframe or whatever large machine that one uses for scientific computation, you still want your application to be running correctly. So you need to pay attention to this. I mean, otherwise it will just be a bug that will be very hard to track if you just deploy your application and some point in time the results of everything you do are not correct. Just because data exchange over the network is not correct. And probably that will be the last point where the ones that are trying to fix the issues will look, because they will expect that, okay, I'm sending a bunch of data from one side to the other and some computations are wrong. And they will first look at the computations and they will look and then probably what has been received over the network will be the last point where they will look to see that whatever they got, it's not the same thing with whatever they send from. So there are CPUs which are using big endian architectures. Okay, what you're telling me is that if I'm using my phone in my PC, it will work. Okay, it will work. But what if you write your code, you put it on GitHub, and you tell everyone, okay, this is the implementation work for whatever method I designed. Take it freely and use it. And you'll have hundreds of guys complaining, okay, it's not working on my machine. It's not working on my machine. Why is it not working on my machine? And nobody will know. Okay, so mostly this is the reason for it. Otherwise, I agree with you. If you know that you are going to run this thing on known architectures, there is no need for this. Would it speed up the things? Just because you're just converting 4 bytes, 2 bytes, and maybe 8 bytes entities, probably not a lot if you skip them, but it will add some. They add some computations, but they are not actually, I think you cannot sense them overall. Now, in order to implement a little bit more complicated, and probably we will stop here this class because I think we will spend the remaining of the time here. Let's take a look at an example of concurrent implementation, threaded server, for the following problem. Suppose I implement a server that generates a random integer number. And then I have a bunch of clients connecting, and each of those clients will try to guess my number. And in order to guess that number, they will randomly generate each one an integer number, let's say an unsigned. And I want your cooperation on this. Each client will generate. It will generate at each turn an unsigned integer, send it to the server, and the server would compare it with its own number, and it will tell back the client, okay, your number is too large. You should send something smaller. Your number is too large. You should send. Your number is too small. Sorry, you should send a larger number. G. This is the code for, okay, you guessed my number, so you kind of win the competition, the contest. There is a contest where each client wants to guess the server's number, and it will send to all the clients that have lost, L, okay, you lost, somebody else guessed the number. So the basic problem that we need to design here, it's some implementation that handles the server generating random numbers and answering to all clients, and the clients that are actually generating numbers, and they are they are, let's say, behaving depending on the answers from the server, they are trying to accommodate. Okay, if they send a too large number, they will try to generate smaller numbers, lower numbers in values, and send that to the server. What do you think it's the probability of a single client to guess the number? Think of it that I have an unsigned int here on 4 bytes, which means I have values from what to what?
From 0 to 2 to the 32 minus 1.
Exactly. This is the range of values. This is a lot. It's a bunch of numbers. 2 power 32, it's quite a large number. And the approach is a little bit similar to, let's say, some sorting algorithm. Do you know which one? The approach I'm taking here. Because if you give each client a hint, you tell it, okay, the number that you have just generated, it's too small or too large.
It works like a binary search.
Exactly. It works a little bit. It's similar. It's not exactly binary search, but it's similar to binary search. Now, how if you're given this problem now, if you were given this problem now, how would you implement this? The first thing we need to think of, do I have a shared state or not? And do we have or not here on the server? We don't care about that much on the client, but on the server, that's the main thing where all the logic is happening.
Yes, we have shared state.
What would be that shared state?
The condition that the number was found or not.
Exactly. So I have a shared state, which means most likely I will implement this way. So this is the first decision that you make. I'm showing you this because Second Lab, actually, it's about this. It's a bunch of problems where you will need to take this decision. For each implementation, you need to tell, is it implemented with fork or with threads, depending on the shared state in the server. So the first question is answered. I have a shared state. I need to implement it in a threaded way. So with this in mind, let's take a look at the possible implementation of it. Oh, come on. I don't want to stay here. Okay, let's stop this. Let's put this down. And let's see why my PyCharm doesn't want to stay down the other side. Okay, finally. So, Python implementation. Just to show you a Python implementation, what a typical client, what you would use in the typical client. Well, create a socket, and in Python, you are a little bit more elastic with the APIs. I mean, you have an API socket, import socket. This is the main thing you should import. And struct. Struct is for converting data from local to network and from network to local. And the remaining of the stuff is just for generating random numbers and so on, so on. But the Python APIs have functions which allow you to create a socket and connect it at the same time to a machine and to a port. And take a look how simple is this. You just specify this pair of things, localhost and port. It throws exceptions if anything happens. By the way, socket error, it's a bit deprecated now in Python 3.8. I think you should use OS error or some different kind of exception. It still works, but in future it might not work. What my client does, it creates a socket, it connects it, it says, okay, I'm not finished, my round is not finished. My start range for my numbers, it's 1. The end, it's 2 power 31 minus 1. I initialize the random seed to generate random numbers. But this is just an incoming welcoming message from the server. So just this is the, let's say, the protocol that I use to implement my application. Is that upon connecting to the server sends some welcome message to each client and prints that message to the output, standard output. And then I count my steps and generate a random number between start and end, send it by convert. This is hash to network long. Take a look at the documentation, struct pack. It takes a number and it packs it as a network 4 bytes representation number. And it reads back a single byte, exactly those codes. It was H, S, G, L, I think. And it acts accordingly. If the server returns age, it says your number is too low, send something higher. Well, I just change the lower bound for my random generator. I just half it if you want. If I want smaller numbers, then I change the higher end to my number. I know it cannot be higher than this, so it should be between start and this number. And if it says, if the server tells me, okay, you win or you lost, then in that case, there is no need to generate any other numbers, and the while loop, and then print whatever decision was. Did I win or lose? Now, this is a fairly simple implementation in Python of this problem. Now, the server side, it's a bit more complex. It's a bit more complex because there is lots of stuff to deal with. Let's hide that. And because this is quite long and I don't want to lose you with the presentation, let's see how it's working first. Let me server concurrent thread. Let me run the server and see. The server, when it starts, it generates a number and then it waits for incoming connections for client, and then it will handle each client. And let's run a number of clients on it. Run 1, run 2, run 3, and we will inspect their consoles afterwards. Okay, so I have each client running in parallel with the number it sent, and eventually I see that at some point in time the first client managed to execute 45 steps and it lost. The second one is the winner with 35 within 35 steps, and then the other ones eventually have lost, of course. This is how it happens. And now I have a few questions for you. What do we need to pay attention to into the server side? I have a server which creates a socket, okay, fairly simple up to this. It binds it to port 1, 2, 3, 4. It listens, and let's skip this part for now. And then there is a while true loop, accept, and then create a thread and pass the execution to a worker. And then is there some intention, start the thread and then count the client. We are multi-threading. What do we need to pay attention to here?
We have to protect the critical region of our code.
Okay, so we have some section of the codes which are expecting to be critical sections. Okay, any other stuff? Let me just hide that so that you answer the questions. Any other stuff that you would handle? Okay, let's take, it's not that, maybe it's not that obvious, but let's take to see the implementation. So the implementation of the main server is quite obvious. Accept, create a thread, append it to a queue, to a list of threads, and start it. Okay, so that will, and pass, that's the function which is called. The client socket is passed on as argument, and let's see, take a look at the worker. The worker. The worker, it identifies itself with the global count. I mean, the global number which tells me when I have the first client that it's 1, then it's incremented to 2 to 3 and so on. It prints a message to its standard output. Sorry, this is the server part with telling client number, client count from, and it displays the IP and the address from which the client connected. And then it prepares a message, a welcome message, the one that we read on the other side on the client. Hello, client, with this number, you are entering the guest competition now. This is the first message that the server sends to the client. And then, while not client guest, which is initialized to false at the beginning, read a 4-byte entity from the client, unpack it, exactly the same thing. Unpack it, it's an integer, and from network to local. Take a look at the documentation of it. I don't want to enter into many details. It's fairly simple. And then compare it. If the number I've got, it's larger than my number, tell it, send, it's larger than my number. Then you need to send smaller numbers in value. If it's inferior, then you need to send higher values. If it's equal, well then, up to here, I don't have any critical section. Is that correct or not? This is my question to you. Pay attention. Okay, now we've seen that the example is working, but we're not sure if it's working correctly. Do I need to put any critical section to protect any stuff up to here?
Nope.
We are not accessing neither. We're not accessing or changing anything global. I mean, there is one thing that we access. It's this client count. Yes. But we could actually, I could put this into a critical section, the incrementation here. But that's the only place, and this one where that is changed. Otherwise, we can assume that this operation, as I'm only referring to this one here, I'm not doing any other operations to it. We can safely start from the assumption that this is atomic, and I'm getting the correct value. I mean, I'm starting from the assumption that the main thread here won't be interrupted in between. I mean, while doing this computation, but in assembly that will get translated to multiple instructions and it won't be stopped in between two things. And even if it is, it will just I will take the previous value here. Okay, so I'm assuming this is correct up to this point here. Up to, where am I? Into the worker, and we were here. If the number is equal to my number, then I take my a locking object, a semaphore if you want, a critical section, acquire it. Once I acquire that in one thread, no other thread will be able to acquire it. I mean, all the other threads that will try to acquire the lock will be blocked here until I release the lock. And what I do, I says client guess true, and I get the identifier of the threading get identifier of the current thread, and release the lock. And then handle exceptions, any communication errors here, and just break out. And this is the point where my while loop stops inside each thread. So my loop will continue as long as no client has guessed. once one of the clients has guessed, and this variable here, it's a global one. Once it's changed in one place, it's changed for all the threads. If the client one client has guessed, and this is executed within each thread, all of them will finish. Well, sorry, all of them will finish because this thing changes and it gets through. And then all of them will be checking, am I the winning thread? If yes, send back to the client, okay, you're the winner. In the server, display a message with the winner. And I'm setting something here, and I will explain this a little bit later. Else, if I'm not the winner, send back to my client, you're a loser. Do some sleep, close the socket, and exit the thread. And that's it. Now, the only thing that is left to explain you is what is happening, and then I'll leave you, or I can. It's all we are already during the break, so I can actually we can do that during the labs or next time. Try to figure out why do I need this set here, and take a look at what E is. E is an event created as threading event. It's cleared at the beginning, and once it's set, this will trigger something. If we look at the main implementation, you see there is an additional thread here bound to the reset server function, and in that implementation, whatever we do, it's while true wait. We wait on that event, and we don't do anything until we are signaled to do something. And this thread, what it does, it joins all the other threads because we need to, and it reinitializes this global state. Why do we need this like this? You need to figure it out. Try to run it. You have the example into the web page of the first or second lab into the not in the first one. I think you have it into the second lab. Yes. Try to figure out why do I need that implementation with an event that gets signaled and signals to the one threads that it needs to take over and reinitialize the state, and what could be a different way to implement this, to pass to a new session. You know, the server, it's still here waiting for new clients. It generated a new number, and then it waits a new round of clients to participate into a contest. Okay, that were the things that I wanted you to show today, and we will continue next time with some new protocol, with a UDP, and we will learn how to deal with UDP part of the TCP/IP protocol, and what are the differences between TCP and UDP, and how do you program UDP. Any questions? And sorry again for keeping you during the break. I will tell Sabina to let you a few minutes. I will call her right away to tell her that I kept you a little bit long. Do you have any questions about this? No. Okay. So in this case, we will be ending this here, and see you guys during the lab and next week. Bye.
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 See you.
Thank you. Have a nice day. Bye.
Have a nice day.
Bye.